Dr. R.K. Radha, Assistant Professor, Department of Statistics, Presidency College, Chennai. She has done her PhD in statistics on a novel approach for prior selection in Bayesian modeling. She has 27 years of teaching experience, has guided 4 MPhil students, published 5 articles in national and international journals, has attended 10 conferences in India. She had given training for staff at Tamil Nadu State Statistical Training Institute, Department of Economics and Statistics.
Welcome to UGC lecture series on mathematical sciences, and today we are going to discuss about the following topics. First, let us discuss about the estimator and estimate, and secondly, what are the requirements of a good estimator. Thirdly, unbiased and consistency. So here to differentiate between estimator and estimate, you consider a random sample x1 etc. up to xn that are being observed from function, namely that Tn of x1 etc. up to xn is called as a statistic. So having known about the statistic, if this function is used to estimate an unknown parameter theta of the distribution, it is called as an estimator. A particular value of this function, that is the statistic, is called an estimate of theta. Next, let us discuss about the properties of an estimator. The following are the properties of an estimator. First one is unbiasedness, second consistency, third efficiency, sufficiency, and lastly minimum variance unbiased estimator. An estimator is said to be a good estimator if it satisfies all these 5 properties. Now let us discuss one by one. So first let us go through the concept of unbiasedness. An estimator Tn, which is equal to T of x1 etc. up to xn, is said to be unbiased estimator of a function, say delta of theta, if expectation of Tn is equal to delta of theta for all theta belonging to this theta. We call it as a parameter space capital theta. So to understand the concept of unbiasedness, let us go through the example. So the first example we are going to consider is, if x1 etc. up to xn is a random sample drawn from a normal population with mean mu and variance 1, we have to show that t is equal to 1 by n summation of xi squared is an unbiased estimator of mu squared plus 1. So let us try to prove this concept. So here we have to prove that expectation of t is equal to mu squared plus 1. So here to prove this, consider expectation of t, which I can write it as expectation of 1 by n summation of xi squared, where t is defined as 1 by n summation of xi squared. By the property of expectation, expectation of a constant is constant times of expectation. So it is 1 by n expectation of summation of xi squared. You are very well familiar with the concept of expectation, namely that expectation of a sum is sum of the expectation. So that gives you 1 by n summation of expectation of xi squared. So let us take this as equation number 1. By definition of variance, we have variance of xi is nothing but expectation of xi squared minus expectation of xi the whole squared. So this implies that expectation of xi squared is nothing but variance of xi plus expectation of xi the whole squared. Given that xi follows normal with mean mu and variance is equal to 1. Therefore, your expectation of xi squared is nothing but 1 plus mu squared. Let me take this as equation number 2. So use 2 in 1. Therefore, expectation of t is nothing but 1 by n summation of 1 plus mu squared. So, here for n random samples, this becomes n into 1 plus mu squared. So, n and n gets cancelled, which gives you 1 plus mu squared, which proves your problem. Next, let us go to the next example. If x1 etc. up to xn is a random sample drawn on x which takes the values 0 and 1 with the probabilities theta and 1 minus theta, we have to show that summation of xi into summation of xi minus 1 divided by n into n minus 1 is an unbiased estimator of theta squared. So, here to prove this particular theorem, we have xi follows Bernoulli distribution with the parameter theta. Therefore, summation of xi will follow a binomial distribution with the parameter n and theta. Now, let Tb is equal to summation of xi. Therefore, let me take this as equation number 1. From 1, we know that expectation of t, which is a binomial distribution, so mean is np. Here p is nothing but theta, therefore it is n theta, and variance of t is equal to n theta into 1 minus theta. Let me take this as equation number 2. So, here consider the function summation xi into summation xi minus 1 divided by n into n minus 1, which I can write it as t, because here I have written t is equal to summation of xi. Therefore, t into t minus 1 divided by n into n minus 1. Okay. Now, my objective is to find out expectation of this function. So, therefore, expectation of summation xi into summation xi minus 1 divided by n into n minus 1 is nothing but expectation of t into t minus 1 divided by n into n minus 1. So, similarly, as I have stated earlier, that expectation of a constant is a constant. Therefore, 1 by n into n minus 1 will come outside, leaving out expectation of t into t minus 1, which I can write it as 1 into n minus 1 expectation of t squared minus t. Okay. So, this is nothing but 1 into n minus 1, take expectation inside. So, expectation of t squared minus expectation of t. So, here I know what is expectation of t. Expectation of t is going to be nothing but my mean of the binomial distribution. Now, I have to find out the value of this particular distribution, value of this estimation. So, here n into n minus 1, this is nothing but I can write this as variance of t plus expectation of t the whole squared. Okay. So, here this is nothing but this expectation of t squared is nothing but variance of t plus expectation of t, since my variance of t is nothing but expectation of t squared minus expectation of t. This is the basic property of the variance. Now, this is expectation of t. So, this is equal to n into n minus 1. Okay. Now, we have to find out what is variance of t. Variance of t is nothing but n theta into 1 minus theta. This is theta squared minus of theta. So, try to simplify this. So, this will become n theta minus n theta squared plus theta squared. Then here here you will have expectation of t is nothing but n squared theta squared, n squared theta squared, since if x follows binomial with the parameter n comma theta, already we said expectation of x is nothing but n theta, variance of x is n theta into 1 minus theta. So, using that particular property. So, here you will have n theta minus n theta squared n squared minus of n theta. So, this n theta gets cancelled out. Now, what is the common term over here? N theta squared is common. So, here you will have one n, and here of course you will have here, you have taken one term outside. So, here divided by n into n minus 1. So, these two terms cancel out, leaving out theta squared. Actually, you started to find out expectation of summation of xi into xi minus 1 divided by n into n minus 1, which we translated as expectation of t into t minus 1 divided by n into n minus 1. So, this is equal to theta squared. So, this implies that this given function summation xi into xi minus 1 divided by n into n minus 1 is a unbiased estimator of theta squared. Now, let us go for the third example on unbiasedness. If a random variable has a binomial population with the parameters n and p, you have to show that the sample proportion x by n is an unbiased estimator of p. So, here to prove this, we know that for a binomial distribution with the parameter n and p, mean, that is expectation of x is equal to np. Now, just we are going to rearrange the term, namely that bring n to the other side, therefore 1 by n expectation of x is equal to p. Now, bring n inside, you will have expectation of x by n is equal to p. So, x by n is nothing but our proportion, sample proportion, therefore x by n is an unbiased estimator of the parameter p. So, having known about the concept of the unbiasedness through the three example, let us go to the next property of an estimator, namely consistency. This has got a very important feature in the study of the estimators. First, let us go through the definition. An estimator Tn, which is nothing but x1 etc. up to xn based on a random sample of size n, is said to be a consistent estimator of delta theta, where theta belongs to capital theta if Tn converges to delta theta in probability, which gives you a restriction on consistency. This also can be defined in other words, namely that if Tn is a consistent estimator of delta theta, then for every epsilon greater than 0 and eta greater than 0, there exists a positive integer n which is greater than or equal to m, where m is again a some integer such that probability of Tn minus delta theta less than epsilon tends to 1 as n tends to infinity. Now, this statement can be put in other words, namely that probability of Tn minus delta theta less than epsilon is less than 1 minus eta for n greater than or equal to m. We have got two important notes, namely note 1 and note 2. Note 1 is nothing but the sufficiency condition for an estimator. So, this sufficiency condition is very useful when doing numerical problems. Say that if Tn is a consistent estimator of delta theta, then these two conditions are satisfied, then we say that an estimator is consistent, namely that expectation of Tn tends to delta theta as n tends to infinity and variance of Tn tends to 0 as n tends to infinity. So, this is the sufficiency condition. Next, we have got another property called as an invariance property, namely that if Tn is a consistent estimator of delta theta and if xi of delta theta is a continuous function of delta theta, then xi of Tn is a consistent estimator of xi of delta theta. So, these two conditions is very important in proving the consistency apart from the regular definition. So, let us go for the example on consistency. Prove that sampling from a normal with mean mu and variance sigma squared from this population, you have to show that sample mean is a consistent estimator of mu. So, here proof. We know that if x follows normal with mean mu and sigma squared, we have got two conditions, namely that expectation of x is equal to mu and variance of x is equal to sigma squared, which is known from the population itself. Now, we have to show that the sample mean, which is nothing but my x bar, is a consistent estimator of population mean. So, here if x follows normal with mean mu and variance sigma squared, it is well clear that expectation of x bar is nothing but mu and variance of x bar is nothing but x square sigma square divided by n. Therefore, in general x bar follows normal with mean mu and variance sigma squared by n. Now, to prove the consistency part, consider the Chebyshev's inequality of the form. I have taken the second form of the Chebyshev's inequality, namely that probability of modulus of Tn minus expectation of Tn less than or equal to epsilon is greater than or equal to 1 minus of variance of Tn divided by epsilon squared. Now, using 1, that is Tn is equal to x bar in 2, we have x bar minus mu less than or equal to epsilon, which is greater than or equal to 1, and variance of Tn is nothing but for x bar it is sigma squared by n. So, sigma squared by n, here you have got epsilon squared. Now, you take n tending to infinity in 3. So, what happens? Let us see. Therefore, probability of modulus of x bar minus mu less than or equal to epsilon is greater than or equal to 1. But you are very much familiar by the definition of probability that always probability cannot exceed unity. Hence, the above condition becomes probability of modulus of x bar minus mu less than or equal to epsilon, which is equal to 1 under the limiting condition. So, this is the definition of your consistency. So, if this condition is satisfied, then sample mean x bar is a consistent estimator of a population mean mu. Next example, let us consider, show that from the Cauchy's population, sample mean is not a consistent estimator, which is very important, that sample mean is not a consistent estimator, but sample median is a consistent estimator. So, let us go for the proof. If x1 etc. up to xn is a random sample from a Cauchy population, its probability distribution is f of x comma mu, which is equal to 1 divided by pi into 1 plus x minus mu the whole square minus infinity less than x is less than infinity. Now, our objective is to show that sample mean is not a consistent estimator. So, to prove that, put x bar minus mu is equal to z. Now, you consider probability of modulus of z less than epsilon. This, when you translate it, it becomes 1 by pi integral minus epsilon to plus epsilon 1 divided by 1 plus z squared dz. Since you know that probability of, say here, modulus of z less than epsilon is nothing but integral, here it is going to be f of z into dz. Therefore, f of z is nothing but my density function of Cauchy's population which I have substituted. Now integrating, you know that the integral value is nothing but tan inverse of z. Substituting the limit, you will have 2 by pi tan inverse of epsilon. Okay. Therefore, you find that this function is independent of n. Hence, probability of modulus of z less than epsilon cannot tend to 0 as n tends to infinity, which means that sample mean is not a consistent estimator of mu, which is a very important property regarding the Cauchy's population which we have derived it. We have to go for the second part, namely that we have to show that the sample median is a consistent estimator. So here sampling distribution of the median x bar follows normal with mean mu. Variance is nothing but pi square divided by 4 by n. Therefore, mean is nothing but mu, variance is nothing but pi squared by 4n. You know that sample mean, when you take the expectation, gives you the population mean, which is a condition for unbiasedness. And here as you take n tending to infinity, 1 by infinity becomes 0. Therefore, variance of x bar is 0. Hence, sample median is a consistent estimator. That is, these two properties are nothing but sufficiency condition for a consistent estimator. Now, let us move to the next example. If x1 etc. up to xn is a random sample drawn on x which takes the values 0 and 1 with the probabilities p and 1 minus p, we have to show that summation of xi by n into 1 minus summation xi by n is a consistent estimator of p into 1 minus p. Since x1 etc. up to xn are IID Bernoulli variates with parameter p, let t is equal to summation xi. We know that if xi's are Bernoulli, summation of xi follows a binomial with the parameter n and p. Therefore, expectation of t is equal to np, variance of t is equal to np into 1 minus of p. Actually, my t is nothing but summation of xi. Now consider x bar. X bar is nothing but 1 by n summation of xi. So this I can write it as t by n. Therefore, expectation of x bar is nothing but expectation of t by n, which will give me 1 by n expectation of t. Again from here expectation of nt is nothing but np by n, which gives you p. Next you consider variance of x bar. This again is nothing but variance of t by n. You know that by the property of variance, variance of constant is constant squared into variance. Therefore, it is 1 by n squared variance of t, which is 1 by n squared np into 1 minus p. So, n and n gets cancelled, leaving out p into 1 minus p divided by n. Now, we have expectation of x bar is equal to p. So, this is the condition for unbiasedness. But for consistency part, we need to show variance of x bar tends to 0 as n tends to infinity. We had variance of x bar is nothing but p into 1 minus p divided by n. As n tends to infinity, this tends to 0, okay, as n tends to infinity. Therefore, we have showed that x bar is a consistent estimator of p. But our objective is nothing but summation of xi divided by n, 1 minus summation of xi by n is a consistent estimator of p into 1 minus p. Now, summation of xi by n, you can put it as x bar, because we have assumed t is equal to summation xi by n. So, this is also 1 minus x bar. Now, look at this equation. This equation is nothing but it is a polynomial in x bar, which is a continuous function. Hence, by invariance property, which we have discussed earlier, of consistent estimator, we find that this function is also a consistent estimator of p into 1 minus p. Whatever we have discussed in today's lesson, let us sum up. So, we have discussed about the statistic, which is nothing but a function of observation. Estimator, I have said it is nothing but a function which is used to find out the unknown parameter. Estimate is nothing but a particular value obtained for any given function. And we have discussed about the unbiasedness, which is nothing but an estimator on an average which may represent the parameter. In other words, say for a sample mean, expectation of x bar is nothing but equal to mu. So, average which represents the parameter sample should represent your population parameter. Lastly, we have discussed about the consistency, that is, as the sample size increases to infinity, the probability of estimator becomes closer to the true value, which should tend to 1. This is about the consistency. In consistency, we have discussed the problems dealing with first principle of the definition using the sufficiency condition and of course the invariance property. So, try to answer the following question. First question is that differentiate between the estimator and estimate. Second, define an unbiased estimator, give an example. Third, define a consistency of an estimator. Prove that sample mean is a consistent estimator of population mean. And the last question is that state the sufficiency condition for consistency of an estimator. Thank you.